It's time to start. I'm going to switch to Notepad. Today we're talking about range and endurance. This is the final section in Chapter 6 that we're covering, and this is the last lecture of the semester. So after you turn in your homework on Monday, you're done for this semester, for this class. So we're talking about range and endurance. And range is defined as the distance flown, usually just the letter R, the total distance flown with the fuel on board. Makes sense. It's just like your car. You fill up the car, you have so many gallons on board. How far can you drive? And it depends on how much fuel is consumed per hour. And that's where we'll get the data for this. It's from something called specific fuel consumption. And then endurance. Book calls it E. I like to call it a time. It's the total time flown with the fuel on board. So for a propeller airplane, things are specified in terms of brake horsepower of the engine. And so we talk about what's called specific fuel consumption. And this is a number that you get that tells you how many pounds of fuel are burned per hour running the engine at a specific brake horsepower. So it's pounds per hour per brake horsepower gotten out of the engine. Makes sense? Because the longer you run the engine, the more fuel you'll burn. And the higher the throttle setting, the higher the brake horsepower, the more fuel you'll burn. So this is fuel per hour per brake horsepower. And so the key feature is that if you take the specific fuel consumption and multiply it by brake horsepower, because power required for flight is something we already know how to calculate. So we multiply fuel consumption by the needed power, and we get pounds of fuel per hour. And then we could flip that upside down to get endurance, which is hours per pound of fuel, to get the endurance. The one thing we have to factor in is the propeller efficiency. So just remember that the power from the engine that's actually delivered is the brake horsepower times the propeller efficiency, eta. And also remember that the power required, which is what we'll be running the engine at to get the right power, is the drag times V infinity. So to get the endurance, we'll invert this and then substitute in for the brake horsepower in terms of the power required. So really, it's just a matter of looking at the units on this specific fuel consumption and figuring out how many hours we can fly per pound of fuel, getting the specific power that we need from the engine. So E in the book, or the endurance time, comes from the hours per pound of fuel which is going to come from 1 over the thing that we just talked about. So the brake horsepower required times the specific fuel consumption. And in fact, the endurance is really the if you're flying at the maximum, or sorry, the maximum hours per pound of fuel. So we're going to call this actually the max endurance. We take the maximum of this. Because we want to say, well, if we just want to stay in the air, how are we going to fly to stay in the air the longest? So we're going to maximize the hours per pound of fuel. And we can calculate that from the specific fuel consumption and the brake horsepower required to fly. So the fundamental formula for this then, for the endurance, is the maximum of 1 over the specific fuel consumption times the power required divided by eta. Because the brake horsepower is just power required. And we know how to calculate power required. It's the drag times the infinity, and we know how to calculate the drag because we've done that for all of the performance calculations. So the range, which is really the maximum range, we don't want to stop short. We're going to say how far can we fly. So the maximum range occurs when we're at the maximum of the velocity times the maximum endurance. Now I need to modify this as not an equal here. This occurs at, so the endurance occurs at the condition where we get that maximum. And we'll actually have to calculate a formula for the endurance and the range based on that. So hang on to that for a minute. So the max range occurs when we multiply the max endurance by V infinity, because V infinity is distance over time. So if we multiply that by the endurance time, then we get the total distance flown during that endurance flight. So really, we just take the formula up here, multiply it by distance over time. So we're multiplying time by distance over time to get total distance, and that gives us the maximum range. So if you look at these two formulas, the specific fuel consumption is just a number. And so really what we're saying is the maximum endurance occurs when the power required is a minimum. So we already know how to do power required plots, so this is easy to find. So let's write that here, the endurance, the max endurance occurs when the power required, we know how to plot the power required for level flight, is a minimum. So this is easy. We plot, or we take our plots that we've already done of power required, and then we look for the minimum. And then how about the range? The range, max occurs when the power required divided by V infinity is a minimum. Because we can take the V infinity up here and put it in the underneath the power required, so we divide top and bottom by V infinity, and then the only thing that changes is power required over V infinity. And when we make that small, we make the range big. And so we can also get this from the power required plot by looking at the tangent line. So fundamentally what we've done is we define this specific fuel consumption is pounds of fuel per hour per brake horsepower, and then we multiply by the power required to do our level of flight, and then that gives us that we can find the velocity where these occur as the minimum power required or the minimum power required divided by V infinity. Okay, any questions up to this point? So again, this is for a propeller airplane. We do our normal plot. This is our normal performance plot. Where we plot power required versus V infinity. And this minimum point then is the velocity that we would want to fly at to get maximum endurance. And then if we draw a tangent line and move it through the origin and move it so that it's just tangent here, then that point is where we get maximum range. And the reason for that is that the slope of this line, because it goes to the origin, is rise over run. So the rise is the power required at that point. The run is the x-axis, so it's V infinity. And that's the thing that we want to minimize from the previous page. And so this tangent line, if we move the slope to get the minimum slope and still intersect the curve, that's where we get that point. So although it took quite a bit of an explanation in terms of specific fuel consumption and all that, once it's all done, this normal power required plot versus velocity tells us, well, if we want to fly for maximum endurance, this is where we fly, and here's where we fly for maximum range. This is very similar to what you did with your glider when you found a velocity to fly at for maximum time aloft to optimize your pilot flying that thing for maximum endurance, essentially, as you found the maximum time aloft. Now, to actually calculate the range or the endurance, we have to take into account the fact that as fuel burns, the weight of the fuel changes because we're using up fuel. And the weight of the entire airplane is the empty weight plus the weight of the fuel. And the reason that that affects the endurance is that the power required that goes into the calculation, the power required plot, depends upon the drag. And we will know that the drag depends upon CL. And then we know that CL depends upon the weight. And so as the weight changes, that changes CL, that feeds into the drag, that feeds into the power required. And so this plot above changes as we burn fuel. So to calculate the maximum range, we essentially have to integrate that term that's the range, instantaneous range of the airplane. So what we end up doing is integrating from the start time to the endurance time. From the initial weight of the aircraft to the weight empty. So this is the weight empty here. And we just integrate that fuel consumption until the weight's all gone. And we get a formula for the endurance time after a bunch of algebra that I'm not going to wade you guys through. And so this is the takeoff weight, and this is the empty weight. So you know the empty weight, you know how much fuel you have on board. You get takeoff weight and everything else you can calculate here. CL over CD is just the lift to drag, so that's a value you can plug in so you can calculate your endurance time. And then the range comes from a similar integration. So you can get the range. So these are the formulas. But just as easily, you could plot the integrand in the integral and then calculate the area under and do this graphically or numerically. So that was for a propeller. What if we want to do a jet? Well, if you remember, for a jet, we always dealt with thrust rather than power. And so that's the only difference is you have the thrust specific fuel consumption. And this is the pounds of fuel per hour per pound of thrust. Similar deal, how many pounds of fuel per hour do you burn when the engine is running at a certain power level or a certain thrust level? So we do the exact same strategy, that the thrust specific fuel consumption times the thrust required, so it multiplies that, gives the pounds of fuel burned per hour. So we're just multiplying by the thrust to cancel that out. And you flip that over and you get the endurance. You get hours per pound of fuel. So the endurance max occurs at a condition where you just maximize that. Max the hours per pound of fuel, and that gives you the most time in the air. So we're maximizing the thrust required times the specific fuel consumption. And then the range occurs at the maximum of the velocity times that thing. Give me a minute, I just lost my screen share. We'll get it back here. All right. So we multiply the top by v infinity because that's distance over time, which converts the endurance, which is time, to distance. And so with both of these, what we do is we plot thrust required velocity, and then we can get the velocity to fly at for endurance, maximum endurance, or maximum range. So the same thing applies, except now we're doing a thrust required plot, which is what we did for the jets. You get a plot that looks like this, and then this minimum here is the endurance max, and the tangent line through here is a slope thrust required divided by velocity, which is what we have up here that we want to try to minimize just like before. And so that minimum slope gives you the velocity for maximum range. And we can do the same integration process to get formulas for the endurance, the max range. Like that. So again, these are the formulas for a jet. The previous ones were for a propeller. So that is the that's the lecture for today. I did want to go ahead, since we have time today, and let's go over the homework today. This is homework number 10. I will post this to Blackboard in case you haven't worked it up to this point, but take notes, and you can follow the notes to get through the homework that's due on Monday. So 6.9 is no problem whatsoever because you're trying to calculate the range of a glider from 5,000 feet. And so you simply multiply the altitude times L over D max, because that gives you the tangent, the angle that goes into that formula. And they give you this. You just simply go back to the formula for the glider that we did a while back in the textbook, and you should get 38,500 feet. So this just gives you a reminder of how you calculate the range. You want to do it at an L over D max. It gives you the maximum range. You should get this number here. (611), you're given the drag polar. Because you're given the aspect ratio, the efficiency, we know pi, and then you're given this. And the hint is to plot CL over CD versus CL. So CD is now the denominator, CL is the numerator. Plot this versus CL. You can see it's a function of CL and CL, so this is an easy plot. And then you pick the maximum of CL over CD from the plot. So you should get a number between 13 and 14. I'm not going to tell you the exact number, but you can pick your max. Should get a number between 13 and 14 for that. Make sure you show your plot and then show the maximum point you picked and state it. So show me the plot, show me that you picked the maximum point from that. (620) is going to be super easy because I decided that you should not do that homework. It talks about the corner velocity, but really it's just looking up formulas and plugging in numbers, and it doesn't add anything to the conversation. So really just the corner velocity is where you get your maximum load factor and structural load. And so it gives you the minimum turn radius from that. So I don't see any value in just having you plug numbers into formulas. So do not do 620. And then the 6 point, I call it extra additional. So this is not extra credit. You need to do this for credit. Is to just follow through exactly what I'm asking you to do. You're supposed to plot load factor versus velocity. So you're doing this plot like I showed you in the lecture, where you get a plot of Nmax versus velocity. And you're getting that from the formula. And you have all the data that goes into there, so all you're doing is varying the velocity and the dynamic pressure. And you're doing this at sea level and 12,000 feet. So the density and the dynamic pressure is the only thing that changes between the two plots. So you'll end up with two plots, one for sea level and one for 12,000 feet. And then make sure you draw in the VNE and the Nmax. And this is just data that you're given in the problem. So add these two lines to the plot of the sea level and 12,000 feet, and you've got your flight envelope. I'm going to allow you to, when you do this in a spreadsheet, I'm going to give you numbers to spot check. So we're going to have velocity. This is sea level. This is Nmax, sea level. And then I'll give you the dynamic pressure for 12,000 feet. And the Nmax for 12,000 feet. So make sure I read across the right row. At 100, you should get a dynamic pressure, 100 feet per second. Should get that dynamic pressure. Should get this Nmax. At altitude, the density is lower, so the dynamic pressure is less. And you should get that Nmax there. And that's the end of our class. Have a good long holiday break. Good luck with finals if you have them next week. And I'll see if we have any questions. Post it on the chat, or verbally you can ask questions. Looks like there's a couple things in the chat. Let's see what's going on. Okay, Kayla, thank you for answering John's question.
No problem.
Yep. Sorry if my writing was sloppy.
Have a good break.
All right. Bye, everybody.
Happy holidays and enjoy the break. See you.
All right.